It was suggested by Abraham Doclala that I create a video that illustrates how to solve an enantiomeric excess problem. So in honor of him, we have a new molecule, doclalium, which has a standard rotation of negative 250 degrees. In the experiment in this question, a 330 milligram sample of doclalium and its enantiomer is dissolved in 10 milliliters of solution and placed in a 15 centimeter polarimeter tube. A rotation of negative 5 degrees was obtained at 20 degrees Celsius. All I care about is how much doclalium is present in the sample. This is very important to be able to figure out how much of the active form of an enantiomer, or the active enantiomer, is present in a sample. And I want this both in percent and milligrams. So let's see what we have in the question. Our two relevant equations are this one, whose job is to standardize. These are standard conditions when we see the square brackets. The job of this equation is to standardize the lab rotation by dividing it by concentration and path length. Units that must be obeyed are grams per milliliter for concentration and decimeters for path length. The reason we have to do this is because we want to compare the lab rotation to the reference rotation, which was done under standard conditions. Reference rotation is given in the question, and it's understood that that is a concentration of 1 gram per milliliter and a path length of 1 decimeter. The mass of the sample is very rarely done in grams in the lab, usually in milligrams, so we're going to have to convert to grams. The volume is conveniently in milliliters already. The temperature is not truly a variable that we are concerned with, but in proper form we should have the same temperature in the lab as we do when the reference sample was done. Path length is supposed to be in decimeters. Currently it is in centimeters. So let's get to work standardizing our lab value. I have converted 333.3 milligrams to grams. You must become experts at doing this. Drug doses are always in milligrams. Balances in the lab are always in grams. Mistakes cannot be made. And in our class, as you know, you are not allowed to use calculators, so numbers with decimals in them are clearly going to cause issues for you. 333 can be rewritten as 1/3. Once again, 0.333 is 1/3 over 10. Converting the decimeters, you can do the math or realize that a decimeter is 10 centimeters, and this is halfway to a second decimeter. So you could write 1.5 decimeters, but once again, you do not want a decimal. So keep in mind, this is halfway to 2 decimeters from 1. 1 is the same as saying 2 over 2. Half is the same as saying 1 over 2. That would be 3 over 2. Now we're ready to solve this equation. In the question, we were told the alpha observed was negative 5.00. We just determined that the concentration is 1 over 3 over 10. and that the path length is 3 over 2. I think we're ready to solve after simplifying. The 3 here in the numerator cancels the 3 in the denominator, leaving a 1 over 1, which simplifies our equation to this. Negative 5 over 1/10. 1/10 times 1/2, which simplifies further to this. Negative 5 divided by 1/20. 1 over 20 in the denominator becomes 20 over 1 in the numerator. Negative 5 times 20 is negative 100. So what we have calculated here is the standardized lab value. Now that this is under standard conditions, it can be compared to the reference value, which was given in the question. We're finally ready to use our percent enantiomeric excess equation down here. So let's set that up. That becomes negative 100 over negative 250 times 100. I believe this number and this number can both be divided by 50, giving this result. You could do further simplification, or just realize that's negative 200 over 50, which is negative 50, sorry. But we're taking the absolute value, so the sign is now meaningless. So 40% is our final answer. All that remains is for us to interpret what 40% EE means. But before we do that, there was an exercise we could have done at the beginning of the problem to determine which is the major isomer. Is it doclallium or the enantiomer? Let me illustrate here. There are only two possible scenarios. Doclallium being major with the enantiomer being minor, or the enantiomer being major and doclallium being minor. It all comes from the signs of the reference rotation being compared to the sign of the observed rotation. The two scenarios are, if the signs match as they do here, then the named molecule, doclallium here, is the major isomer and the enantiomer is minor. If the signs of those two numbers didn't match, then the named molecule, doclallium, would be the minor isomer and the enantiomer would be major. So clearly, we are in the first scenario in this problem with both signs being negative. Now we can interpret what 40% EE means. When you have a 40% EE, the solution behaves as if it is only 40% pure in the major isomer. Why is this? It's because the other 100 minus 40, 60%, is a 50-50 mix of doclallium and its enantiomer, and that portion of the solution does not rotate light. So I break it down as 40% EE means 40% major, plus the other 60% is racemic. That breaks down to give us 30% more each of doclallium and its enantiomer, as illustrated here. So our final results in terms of percentages, 70% major, which is doclallium in this problem, 30% minor. Our last job is to convert, without a calculator, 70% into milligrams, keeping in mind the total was 333.3 milligrams. This is easier than you think. 70% can be broken down to 50% plus 10% plus 10%. The hardest part of that is figuring out what is 50% of 333. With a little work and no calculator, 166.7. The easier math is the 10%. You take the total, slip the decimal one, and you have 33.33 and another 10%. Do that again, and then do your long addition. And you have 233.36 milligrams of doclalium. So 70% corresponds to 233 milligrams with 3 sig figs, and our final answers are in our box here. Congratulations, you're done.